have Nachiketa Acharya here today, who is an expert in statistical and machine learning approaches, specifically in climate sciences, focusing on subseasonal to seasonal forecasting. He's a member of the series NOAA collaboration, specifically in the NOAA Earth System Research Laboratory, Physical Sciences Laboratory. He previously held positions at the Department of Meteorology and Atmospheric Sciences at Penn State, the International Research Institute for Climate and Society at Columbia, the Institute for Sustainable Cities at the City University of New York, the National Center for Medium Range Weather Forecasting in India, and the Indian Institute of Technology in Delhi. He's actively engaged in several regional climate outlook forums, where he's involved as an expert and trainer of S2S forecast and verification. Thank you so much. We're happy to have you.
Thank you. Thank you, Jennifer. Thank you, Chelsea, Christian, for this opportunity. So I was thinking it's a great opportunity for me to kind of spread my wings from NOAA building to the other part of series. And I just came to know just labs. So this talk is about like my work in climate prediction and prediction, but I use a approach called research to operation, then back to research. Like mostly people are like R2O, but I just added because all the research I do is involves so much with the stakeholders' involvement. And sometimes as a scientist, we thought, oh, we solved the problem. But when you apply the problem, you understand, oh, you have a lot to do. So I always get constant support from my stakeholder counterpart. So that's what I put in here. So thank you, Chelsea, for a good So thanks, Claudia, but I just disclaimer. Yeah, it's a real accident. You know? It's a story itself. So I was a master's student in theoretical statistics. My special paper on actual statistics, which is the background of insurance. I did a lot of theoretical, distributional kind of things, but life's changed. Then I kind of ended up with learning this thing. And I think like back in India, where I did my master's, like people still thought like a statistician should be in insurance field or a biofield, like biostatistician. It's like nobody knows about climate. Me neither. So we kind of accidentally learned about that. And with all my, journey since 2008 to now, I became a climate data scientist. And thanks to my collaborator, colleagues, and students, I learned so much. And I always like collaborate with the people from the atmospheric science or meteorology so that I learn a lot. So as I already explained, like my approach, and I use these 4 bubbles, so like I like that. So as a core, I'm a scientist. At the same time, I also do a lot of operational forecasting. That's kind of a part of my research that where I develop something and it's an operational forecast, and then I get a feedback from the stakeholders, as I said. But while doing this, I kind of understand there's a gap between the science and the stakeholder application. So we call capacity building. And that's what I do a lot of when I call the Climate Outlook Forum, which is a WMO forum where there is a forum where you can talk with the stakeholders, try to for example, a crop modeler or an agriculture scientist need a forecast for what will be in next 300 days every day, which is not possible. So like teaching them which can be predictable and which cannot. So yeah, so we kind of fortunate to travel all over the world for this capacity building. A little less now, last year when I joined NOAA, but yeah. Anyway, so let's start with prediction and projection. And as I know everybody in this room may understand this difference, but just for sake of understanding, like projection means, as you all did that, like what will be the climate in next 200 years and different scenario, this and that. CMIP6 model, kind of a very popular term nowadays. But when I say the climate prediction, which is a little different, which is like what will be the season, like what will be the winter, what will be the next spring. This is also called a climate prediction because it's not like a daily variability. It's a kind of a, average, long-term average of weather, in terms of a time period, which is maybe 3 months or 1 month or 2 weeks. So that's what we call like S to S, which is sub-seasonal to seasonal, which is like, it starts from after the weather forecast of 5 days, it start after like 6 months. So that's kind of thing we're talking about climate prediction. So climate prediction is something like my core, research. But during my postdoc at City University of New York, I do a lot of climate prediction. And I thought like it might be good to start with that. But before that, again, I kind of, putting all those and try to explain. But before going to the work, I want to explain what is statistical learning means and how I ended up with that term. So statistical learning is a theory, is a framework for machine learning drawing from the field of statistics. So, we talk about machine learning, deep learning, a lot of different learning nowadays, but as a student of statistics, you kind of pick up those learning, which is very similar to the statistical background, except that, it comes from the image processing. So that's what we kind of, blend the statistics and machine learning and create that statistical learning. It's a lot of, data mining and all those things. But again, it might be very fancy word nowadays, but, it was like a very common thing when you, study our statistics, like applied multivariate or time series analysis. Like these are the things we learned from our class. So here, like a little bit of, as I said, like I want to share my experience here and get the feedback. So here is my journey. Like after masters, I was working something and I kind of suddenly know about this term called machine learning or deep learning. And throughout this talk, I kind of switched the term machine learning and statistics. I don't want to put it a specific term. So I was thinking, and then, I was a big fan of sci-fi movie. I was thinking about it. Then started reading about, human robot. And it's a very fancy, especially when it comes to local newspaper, that AI will be changing the world. And I'm talking about 2008, that time. It's a very fancy scientific sci-fi term. Then I started talking with a lot of people. And not only my field, like I talk with engineers, electrical engineers, civil engineers, and hydrologists, and that. And everybody has a very unique way to explain it. And I kind of remember one story which my mommy used to read. It's like a story of a blind people who try to find what is elephant. I don't know if you know the story. There's a 7 blind people and they goes to and they touch elephant and they said, oh, elephant is like a trunk or elephant is like a beam, something like that. And exactly happened with me. We were like, oh, no logistic regression. It's like very, back in 2008, there's no course on that. But then I kind of self-study all those things. And at the end, this is my conclusion. It's like, okay, so this is a statistics. Okay. So it's not new. We know everything. Anyway, so that's my journey. And still going on. I don't know what I explore in the next, maybe something else, maybe mathematics instead of statistics. So, okay, let's talk about what I will discuss today. So there's a 2 research project. One is kind of a climate change scenario for which I developed for New York City drinking water supply system. And it was like my postdoc at City University of New York in a Department of Geography and Sustainable Cities, just like 1.5 years. And then next, talking about very close to my core research with S2S prediction. And this is one is for the global, one is for the regional. And in fact, I was thinking what to present yesterday. I was thinking let's focus what I have developed up to now at NOAA instead of telling last 15 years of my research. And again, as I said, the approach is nowadays people take that approach, but my approach is very, try to learn the core science and then find which method should work. So, okay, so let's start the core. The generation of plausible climate change for bottom-up approach, a lot of different terminology. Let me explain one by one. So maybe some of you know, New York City water supply system is very unique because all the drinking water comes from the upstate. And that comes as a gravitational pool, very less processing, just a very minimal processing, because they want to raise up this whole upstate, this part, instead of, making this lab to process the water, they make it reserve and that's the way it works. But if you can zoom, it's actually 6 reservoir adjacent, and they have like, I think, I don't know, like maybe it starts since 17th century or something. It's really going on. It's unique way. So why they are interested in climate change? So New York City is very different than the western part of the country. Like they are always blessed with the rain and storm. So there's no issue of having less water, but there's an issue of the potential effect of this change in precipitation, including increase of sediment erosion or nutrition loads and change of annual cycle. And I was, because they put me on this place and I lived there, and there's like every time there's a storm, like, the forest, the tree breakdown on the watershed is like the water quality is like terrible. So they are kind of interested in the water quality, not the water quantity that much. So my, like before I joined, they have started that work. And, mostly we talk about climate change scenario. The thing comes from traditional approach, like, there's a climate model, you downscale it and, just find different scenario. And that was, they call top down. And like people before me, they do a lot of different things. But one of the biggest problem, like this particular area, this watershed is like only, I think, 4,000 square kilometers. So thinking about a climate model grid size, like it's like you cannot find one grid. And then you do a lot of statistics, you're adding this noise. So they kind of understand the problem. Then when I join, they start like a experimental system, which called BottomUp. So it's basically, the whole idea comes like not all climate model kind of provide the full range of uncertainty. Instead of top down, why don't you think about the bottom up? Think about, whatever you have in the ground, the observation, you use that, and then you make your own scenarios. And also, while doing this, you incorporate the experience of the hydrologists who are working, last 20, 30 years on that field. So that's what we call a bottom-up approach. So there's a lot of different way to do it. Like one way to do it, or one tool is called stochastic weather generators. So what is stochastic weather generator? Like, I try to explain in a very simple way instead of equation. So suppose you have a climate data for a particular station, like rainfall for last 200 years, or temperature, or solar radiation, and you try to make a model, statistical model or machine learning model, so that you kind of fit all this data. And now when you have a model, you can change the parameters of the model and making different scenarios, just like a climate model. You set a climate model and you change the forcing and run different scenario. Here, the good thing is it's much cost effective, because it's just like a piece of code. You don't have to run this whole climate model. So just a little bit of, it's not like something like we started with, like, people from 18th century say, they also work on that. So especially the toughest variable to deal with in this stochastic weather generator platform is rainfall, because rainfall has a two different process. One is like occurrence process, whether it's rain or not. And then if it is rain, how much is rain? So think about a random variable have two different nature, discrete and continuous. So it's kind of a two-stage model. So first stage modeling people use very popularly called Markov chain. It's kind of a probability theory, like the probability of having rain of today, it's actually depending on yesterday or day before yesterday, and you go back and you kind of increase the memory on that way. Once you have that, then you fit different kind of distribution, where the rainfall goes very, skewed distribution, because most of the daily rainfall doesn't have data. So you go for gamma, beta, so many different ways you can deal with that. So before start this research, I was like doing a really good literature review. And that's the part I really like in my research, because reading is like my passion, and it's very easy. Like you don't have to do research, you just read what people do it, right? And then top of that, you're getting your salary. So you're just reading. So I love that part. So I kind of do a lot of literature review and find the goals. The goals is like, first, we need to make a weather generator based on that data we have. Once we have the weather generator, we should run the watershed model using the scenario from the weather generator. But before going to climate change, we need to make sure that we capture the history, like past climate, just like climate model you do, like we do diagnostic. And then when you are confident, you make a different future generation. So that was like 3 goals I had during my postdoc. And the first goal is something like, my expertise of statistics. I was thinking about, let's do whatever I learned up to now, let's do it. So, different order of Markov chain, different parametric distribution or resampling or curve fitting, da, 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 da. And then I'm not going to explain all those things, just to know, like, we kind of do a lot of result, like skill evaluations, like, which Markov chain order is good. And we found because there's no pattern of rainfall in New York doesn't have a rainy season. It's like almost every day you get something. So you don't need a memory. Like if there's a rain yesterday, you can predict it. So that's what we found, like Markov chain of order 1 maybe okay instead of 3, 4. Once we've done that, then we kind of, use different parametric approach and non-parametric approach to find the descriptive statistics of the rainfall, whether it's captured the mean, this and that. And what we found, all the parametric distribution captured the mean median, and which they are not interested. They're interested in the extremes, right? So that's what we started like adding, thinking about plotting the CDF in a log scale to find which distribution captured the tail. And then we also calculate this, IPCC definition of RX1, which is maximum rainfall. And let's compare which distribution take it. And then at the end, using generalized extreme value distribution to find this return period of the flood, like 50 years, 75-year, 100-year flood, because they tried to make a scenario at that time on like 65 years. So thinking about which method works. So after doing all those kind of different skill analysis, we found that Markov model with 1 degree and skewed normal is the best option. And then we kind of make the scenario from weather generator and we run a watershed model called generalized watershed loading function. And then we kind of predict the stream flow. But before making this future climate change, which I'll come later here, like think about the first part, like make a historic climate, and then we kind of run 2 different simulations. One is like running this stream flow using the actual observation we have in 60 years. And then we run the watershed model using the synthetic data from the weather generator. And we run for different watershed. And this is like an annual stream flow. And we found like, while you're running the watershed model with the synthetic data is as good as you're running with the actual data. So that means our statistical modeling is kind of success on capturing the statistics of this last 60, 70 years. So once we have that, now we're thinking about how to make the scenarios. Now here, I want to spend a little bit more time here, like the way we make that decision. Think about, Excel set and the y-axis like changes in precipitation and x-axis like changes in mixed temperature, max or mean. So thinking about the baseline, like where you have 100% of rainfall and no changes in temperature. Now think about you increase or decrease that scale. Like let's decrease the rainfall or let's increase the rainfall in a percentage and also increase the temperature or decrease. Now the thing is like, you may ask like why 0.75 to 1.25, why -1 to 6? How you kind of get that, subjective scenarios. And that's what I talk about, like stakeholders involvement, like people who are there, running the hydrology model, working 20, 30 years, they kind of see everything, 1972 drought to like recent, things. So they thought like, maybe this is our bound. We can also think what climate model gives us. So based on that, we make a 3D plot. Again, it's pre-Python age, so it's a MATLAB plot. Maybe I can make good plot now. So think about, again, the x-axis is like precipitation, y-axis is temperature, and we run the stream flow. So whatever you see, the shade is actually the stream flow. Now we are putting that lot of historical information, whatever in 1970s drought and whatever was 2000 flood. So those are like different color set are like the real observation happening first. And all the red dots here are climate models, which we downscale using the traditional statistical method. So think about if you don't have this like full cone of uncertainty, the climate model only shows a like increase of things. But there is an incident in 1970 was a drought. So we try to capture all different scenario. We don't want to miss it. So based on that, again, we run kind of stream flow and they make their 65 years climate change thing. So that was excellent. So we kind of do, and we are so happy, this and that. And again, like research to operation we done. And then when we explain this thing to our stakeholders, which is New York City government, and they said, oh, that's excellent. But you know what? If there is a storm come, it doesn't come one watershed because it's like 4,000 square kilometers. It's actually go for the others. And all our modeling up to now, we did independent of each watershed. So we kind of forget about that spatial, connection. So that's come like, again, like you want, one way, forget about something else. And that's what the limitation comes, like how to keep that spatial correlation. And that's heat map is like the precipitation correlation among the watershed in 6 watershed. So they have really strong correlation. And obviously it should be because it's a very small thing. And we kind of doing it independently. And unfortunately, after that, I joined Columbia University. So, okay, you deal with that. That's a problem is always in my mind, like how to deal with that. And then like recently I was reading something and I feel like, oh, maybe I can use it. So the way I was thinking this problem now and doing it my like weekends or night, not my time at whatever I do. Thinking about like there is a method, I don't know, some of you know about this called generative adversarial network. It's a very interesting deep learning method which developed in just the last 10 years back. And I just quote one things from John Lucan, like director of AI of Facebook. And he said like, that's like phenomenal discovery. So the way it works, it has a 2-part, one called generator, one called discriminator. So think about there is a discriminator who know the story. Like, for example, this guy know how the real Mona Lisa picture look like. And I start making a Mona Lisa picture. And I thought, like, I can fool this guy very easily because he don't know. But actually he knows. So I start making my Mona Lisa and give it to him. It's like, oh, it's totally, just revise it. So depending on his feedback, I go back and try to make it. So kind of getting a teacher who tell me which I make my Mona Lisa from a kind of a fake data. So basically, this is a very interesting thing, but mathematically what happened, if again, I know I don't want to take a mathematics class here, but it's basically a min-max problem of 2 different functions. One part is try to, maximize, which is the discriminator that who know the real story. And one they call like the thief, which is he wants to, kind of fake that guy. And if you take 1 minus of that, is again a maximize the problem. So basically, it's an adversarial game between 2 functions. Try to find something which is very real, but start from the noise. Start from the noise, it goes to real. So think about the same idea in here. Earlier, I explained we have a data, we fit different statistics and make a model. However, we start our model from the noise and then make a weather generator. What is the gain on that? First of all, there is no parametric assumption that rainfall follow gamma distribution or beta distribution or whatever. And also, it also keep that the relationship among the different watershed model, spatially, and also weather generator is not only for rainfall, it's also produce rainfall, temperature, solar radiation, and wind. So I was thinking about correlation between those variables also important. Right? You cannot make it like wet day and high max temperature, right? So keeping that correlation between the variable and the space, I think that method maybe works better. And that's what I started like playing with, data I have and like the box plot of actual data and then the synthetic data and the kind of, doing the basic things, but that's not something I want to achieve. What I really want to achieve is like this, like the actual correlation between the watershed. And now I have again generated synthetic data and I got that correlation. Again, it's not a perfect because, it's modeling. It's also whoever in a AI ML, like there's a term called hyperparameter tuning. So you can tune your model. And I don't want to do any hyperparameter tuning right now because I want to see like what comes without tuning. And that is kind of without hyperparameter tuning and giving me a very good hope that, yes, if I do a lot of hyperparameter tuning, maybe it will be more close to that. So that's kind of thinking. And I recently talked with this to my, old collaborator and like, oh, that's good. We can use it. So this is something on the generation of future projection and kind of a little remarks that we start with the idea called bottom-up, which is different than the climate model downscaling. But we use this weather generator, then we found there's like, we need to incorporate the spatial correlation. And then we just use very, sophisticated method and just kind of using it. And we got it like, yeah, it's actually taking that whatever we wish for. So that's kind of the first part of my talk. But before I go to second part, do you have any question? If not, it's fine because there's a lot of information. Yeah, go ahead.
I was wondering if you could talk a little bit, going back to your comparison of the observed stream flow and the synthetic stream flow. It looks like your interquartile ranges match really well, but that the synthetic has a lot more extreme values. I was curious.
This one, right?
Yeah.
Yes. That's kind of thing happened. So what happened here? Like we kind of, I can show you one thing so that it actually helps. When we make this weather generator, like all those traditional distribution, like exponential, gamma, and other things, they kind of very well to predict the central tendency, which is mean, right? But we are not interested. So then we started along like kind of combining the distribution, like skewed normal or mixed exponential or hybrid exponential, but in the tail is generalized Pareto. So while doing that, we kind of getting that because we try to predict the mean, but we also try to predict the extremes, and we get a lot of new extremes. So it was not in the history. Like these are like so many, as you said, like it was not in the past, but it was a lot of new extremes. And when we explain this thing, and some hydrologists like that because they said like, you know what, like we want to make a future scenario which will be very different maybe compared to past. So having some weather generator which can able to generate the new extremes is good. So they kind of happy to keep that kind of extreme which is not in the past. Because there is other method, and at least here, in fact in CU Boulder, there is a professor called Balaji Rajagopal, if you know him, like civil engineer. Balaji is like a fan of Balaji. So he used a method, exactly same thing. And I keep that and I show Balaji that my method is better than you. I was like, no, my method is good. But they use resample. So resampling, basically you have like 60 years of data and you resample the data. And it's very good to capture the mean, but what about the new extremes, which is not in last 60 years? So that's what we kind of keep that like purposefully to have, we are okay with having new extremes, but thank you for pointing it out. Okay. Any more, or I should? Oh yeah, go ahead.
So with the adversarial networks, in thinking about applying it to projections, you don't have truth with which to set up that adversary. So how are you gonna train, especially if it's out of kind of sample sort of events that you don't see in the historic record? How would you apply that kind of method to like future projections?
That's a great question. That's kind of, so the way it works right now, it's a data driven, right? So whatever the data you give, you'll test, you know, and you have to also set your target. And my target was like keeping the correlation, having the rainfall, having the temperature. So it's kind of very good in last 60 years. Now, as you said, like how you generate the new scenarios. And that's what I use, the exactly same idea of what I did for statistics. Like think about all those different scenarios, like 1 degree, 2 degree, 3 degree. And I kind of resample the data input in a GAN. And there is actually, I would say more on that. So there is a vanilla GAN, which I explained here. But the GAN I use called conditional GAN. So I can condition the GAN which he wants to make the target. So I condition that you add 1 degree more in temperature, or you add 25% less in temperature. So you can actually condition. It's kind of a conditional probability concept. You condition something, and then you can say you again like do it. And the good thing here, like, you know, all deep learning take a lot of time for training. But once it's done, the future scenario is like a second, because it's not training again. It's like everything he has, he just, you know, makes the generation. So we are kind of using the conditional GAN and changing input so that it will be more, you know, warmer or more wetter. Thank you for the question. Yeah. I kind of purposefully keep the heavy stuff back because each of the heavy stuff can take water. So thank you. If not, let's talk about something different. So we talk about climate projection, that's excellent. And now talk about climate prediction. So the climate prediction is kind of a, you know, probabilistic prediction of what will be next season or what will be next 2 weeks kind of things. And why probabilistic? Because the uncertainty. We are dealing with something which is extremely tough to predict. And any prediction have a predictability, right? Like for example, stock exchange, you know how far you can go. Or finding like, the Netflix or Amazon, like they kind of have their search based on your previous search. So they know like what. So it's kind of the predictability point. So before I go to any kind of math, just to let you know what the predictability comes from seasonal food. And we may all know about these two terms called El Nino and La Nina, which is the event in tropical Pacific. Like if it is warmer, then it has a different impact on the whole climate. And thinking about our Earth is a globe of the water, it has a lot of impact. I'm not again expert of this whole atmospheric science component, but the way I understand, it is a triggering effect. Like if right now it's a El Nino, and last year it was La Nina, and we know like how it's impacting in US climate, but it has a huge impact on in the global perspective. So that's what, like, if there is a ENSO, or like they call El Nino Southern Oscillation, if you know there's going to be La Nina or El Nino, it's very easy to predict because like, the connection. But if it is not, if it's a normal, it's very tough. So seasonal prediction is really tough. And top of that, I add a little more tougher problem called sub-seasonal prediction, which is beyond the weather scale, like weekly average. And there's a lot of different factors. One of the factors called Medel-Julian oscillation. This is an eastward propagating wave, and it's actually it's in the tropics, but it has a lot of impact. Interesting thing is this Medel-Julian. So the Medel is actually from NOAA, and I met him in one of our NOAA picnic. So anyway, so that like two different source of predictability of two different scale, and which is hard to predict. Now, again, what do you expect? I found this interesting cartoon, like what do you expect your scale of forecast. So it's like after 5 days, as good as your random. But basically, while I was at IRI and working with this whole H2S project, we make this subjective diagram. And let me explain the diagram. So the x-axis is like the forecast range, and the y-axis like a subjective skill score, like 0, poor, fair, good. If you look the first, like start with excellent to come down, which is the weather focus. That means you want to predict what will be tomorrow, day after tomorrow, and go on up to 10 days. Like you want to predict the state of the weather for each day independent. Now, let's look here before we go to weekly. In a seasonal scale, what you want to predict? You want to predict the average weather, right? What will be the summer? That doesn't mean like what will be the everyday of summer. Like whether it will be like normal than the warmer or less than the warmer. So while we are kind of smoothing this chaos in the weather, you have a little bit of skill, but that's kind of fair skill. But thinking about this, which is between weather and season, sub-season, which is, it called predictable desert because it's very tough to predict because again, MGO is one of the signal, but not the signal. There's a lot of different things, and people from the atmospheric science and oceanography, they still kind of research on that, like how to improve the prediction. So just to let you know, like what I'm going to predict here, so you can imagine my prediction scale. So let's a little bit like, okay, so whenever you talk about climate prediction, there should be so many different ways, but since the first prediction in 17th century up to now, they have like two schools. One is like statistical modeling school, one is like dynamical modeling school. So statistical is kind of, again, nowadays fancy way to call machine learning school. So suppose you want to predict something which have a long time series, you can just do it like the way I do set up the weather generator. But or if you know that there is a guy called El Nino or La Nina, it has an impact, just make a regression. Like whenever there is something, you can do things. But that doesn't work. There's two reasons for that. First of all, the autocorrelation or year-to-year variation of rainfall especially is so chaotic that you cannot predict it. And second thing is like this relationship. There's a huge thing going on. So we know there is a relationship between ENSO and rainfall, but that relationship is not constant. It's also changed because of climate change. Like in 50s, I read that paper in 50s, if there's El Nino, there's a big drought in Africa and Asia. But right now it's El Nino, and I'm from India, so there's a flood going on. So it's very different. The relationship is also changing over the time. So we cannot use basically statistical modeling. But with a huge improvement understanding of physics and having the computer resource, people make these dynamical models. And what is dynamical model like? I'm sure, like, I'm not a subject matter expert, but you know much better than me. But what I understand is you kind of make a grid over the whole globe, and every grid you calculate the law of physics. And then kind of this equation is go, side by side, and it involved chemistry, dynamics, fluid dynamics, and all those things. So ultimately, it's try to mimic the whole Earth, right? Earth atmosphere or Earth ocean. And there's like a couple model which also like take care of the ocean part. So basically it's a computer thing, but again, a little bit of chaos theory, you all know, like you start with something and end with something because of the Lorentz chaos theory 1963. So whole point telling here that when you call GCM or general circulation forecast, it's not a one product. It's like an ensemble of product, because depending on the initial condition or boundary forcing you give, there's a little bit of idea. But if we have that tool, then what is the need of doing something else? So these are again a very and I'm a very graphical person, so I try to understand everything on graphic and try to explain in graphic. So think about, suppose the blue line here is some kind of observation, and all those black or kind of gray is like different simulation of the climate model, and you can literally see a bias, and you can see, oh, it's a very easy, like it's a mean bias, just take it out. When you take it out, the mean bias, the scale is changed, but if you can see that ups and down is not same. So like when you do a bias correction of GCM, it's not that you try to bias correct the mean error. Rather, you try to bias correct such a way that is also captured the ups and down. That's called the whole uncertainty things. But again, in a statistical point of view, think about you correct to PDF. PDF stands for probability distribution function. Instead of mean or variance, you try to kind of match these two PDFs such a way that it's kind of giving you all the ups and downs and point to the mean line. So that's what like whole thing I was thinking about, like how to do the post processing. Now, traditionally, it's not, I'm the only person to think that, like again, last 50 years, people do it. At least has a different way to do it. One non-parametric. Think about different ensemble members. If you run your climate model for 80 ensemble members, you can calculate the probability of any event based on the counting of the members. For example, you want to find like probability of above normal rainfall. So, and if you know your definition of above normal, you find how many members follow on that bin, and you just count it and calculate the probability. That's called non-parametric. Parametric, again, fitting different distribution. Most of the cases, people use the Gaussian distribution. So if these two methods are available, then why we need machine learning or statistical learning? Because they have a limitation. Think about you have very fewer ensemble members. Suppose you have like 5 ensemble members, which is a very common in subseasonal scale because it takes a lot of computational power. And you have a 5 ensemble member, you want to predict 6 different categories. So some of the categories you don't even have these members, so you cannot calculate the probability. For the parametric, as I already explained, like assumption normal distribution is kind of killing me a lot, because people thought, oh, it's all everything is central limit theorem, but it's not, because you are dealing with only 20 years or 30 years of data. And top of that, you need to first make the deterministic forecast and change and convert it to probability. So thinking about that, I was thinking that, no, we should do something else. Now, before going into machine learning, the very benchmark model we use in our statistics or machine learning called logistic regression, right? So logistic regression is a regression where the input is continuous data and you ended up with classification, like whether it's above normal, below normal. So we can use that logistic regression very easily. But what I found while I'm doing that when we setting this logistic regression, it's like depending on the category. So suppose I need to predict like 5 different categories. So I need to fit 5 different logistic regression. And once I add all those output, it doesn't give me probability between 0 to 1. There is a way, because it's no information about the threshold, it give me like 110 or minus probability. So that's what I kind of adding one function, which is the function of all the quantiles, and called extending logistic regression. So it's a logistic regression, but it gives you the full probability distribution, except each category. And well, I was working at IRI, Columbia University. I kind of set up in 2017, and still they are using that method. So making this whole seasonal prediction and substitute. While joining NOAA, I was thinking that, okay, so if I have this thing, why not I implement it here? But then I was thinking this method a lot, and I found two limitations. One, it takes forever because logistic regression is the way it's solved. It's kind of using the iteration. It's taking a lot of time. And secondly, we implemented for this rainfall and temperature, but for temperature, logistic regression is not appropriate because we found like it doesn't have because temperature is more on Gaussian. So we try to find something else. So then I thought, let's do some machine learning. And again, the machine learning is not one model, as some of you know, it's like so many different learning. Then I found like, okay, so which learning is connected to this problem? Then you found supervised. Under supervised, there will be like regression classification, then maybe it's regression. And if I put regression, there's like 1,000 regression model. And I just took some of them. And then there's the method I really like, which is neural network. But when I say neural network, and then you have like so many neural networks. So there is like always a choice problem. Which one you want to choose? And that choice should not come only the problem, also depend on your resources. So I'm not like blessed with GPU and 200 people work under me. I can do whatever I want. And top of that, the sample size, which is the biggest issue. Because suppose you try to use a fancy deep learning and you have only 30 data points. You ended up with overfitting, right? And all those big tech gurus like Facebook, Google, this and that, they are taking all the data from us. That's what like, you know, like whenever you install an app, you kind of accept everything because they want that data. And in this case, we don't have. So I was thinking of all those things and then find out a method. And, you know, that's my approach again. I keep it simple so that you can run it quickly. It's a real-time forecast. We don't need, and that time, NOAA PSL doesn't have GPU. So I kind of set up everything in CPU system. So I use a method called extreme learning machine. Extreme learning machine is kind of a very generalized way to set up the single middle layer fit for a neural network. So again, I don't want to go a lot of math, but the way neural network works, it starts with the random weight and bias. Then it goes different layers. Here, one layer because it's single layer. And then it goes to output layer. And every layer is also have the activation function. And it's kind of estimate a target. And then it compare with the what kind of their output. And if it is not, it go back. And again, update the weights. The way it's termed, it's called backpropagation. So it's kind of, you know, start with just something, or it's not, again, go back and try to set up and again, go back. It's go forever until unless you have a stopping criteria that, okay, I'm okay with that. But those kind of backpropagation also take forever in terms of calculation. For this particular method, it doesn't go backpropagation. It's rather start with like a random bias and all the calculation done in hidden layer. And that's kind of a math on that. And once it done there, it kind of like fix. It doesn't have this whole time of backpropagation, and people done a lot of different research, whether it's as good as neural network or as good as other method called support vector machine or this and that. So it's kind of a long story. So, but what happened? This is like a vanilla neural network. Think about X1, X2, Xn are different GCM input, and you want to predict the Y. But by default, this method giving you a deterministic focus. That means amount, rainfall amount. But we want to make a probabilistic focused. So on that, I kind of change the whole network, and instead of one output, I make it 3 different output. And 3 different output is a probability. So probability of above normal, below normal, near normal. And I thought, okay, the problem is solved. But while working here at NOAA PSL and the project I'm working called Fuse that I've come on next slide, where people are interested on the extreme, like what will be the extreme in next season? And this 3 category doesn't give the extreme. And then again, the stakeholders involvement here, like stakeholders said, oh, you give above normal, but your normal definition and my normal definition are same. Above normal, how much above normal? So we thought about instead of 3 category, we make the full PDF or full probability of distribution. And I call this called extended POEL or whatever. So we're still working on that and writing a paper. So kind of using a available structure of network, and we kind of change the network depending on the problem we are solving and having the feedback from the stakeholders. And based on that, this is the project I'm talking about. It's called a famine early warning system. It's a big project at involved US, like I think it's USA project involved NOAA Center, I think University of Santa Barbara and so many different things, and NOAA has one thing. So the whole target, like giving the early warning for the food security. And when I joined, the PI from this part, he was like, can you join me and make something? So on that note, we make this whole website. And this is at, it's actually online since last April at NOAA website. And here we make different things like seasonal forecast, monthly forecast, 3-category forecast, probability of extremes, and also keeping the scale of the forecast. Like most of the cases wherever, for example, you open your phone app and see whether there's a rainfall in next hour, right? But you don't think that whether it's a reliable forecast or not. I also add that part here. Like people have forecast, I also have the reliability part, like the scale. Now you take your decision. Like I give 70% rainfall having this scale, so that it's easy to take that decision making. So the way it's set up is a lot of things. We do a lot of data crunching, and I talk about that. Like we don't have much support. Like it's me and other person, and kind of developing this whole database and making this thing. Blah, blah, blah. But a little bit of skill comparison of all the different methods. That ELR is from IRI. This pack is from NOAA CPC. CPC stands for Climate Prediction Center. They have a method. And we kind of compare it to different skill called ROC and reliability. I don't want to go that far, but one thing I want to explain here is like lead-wise scale. That means what stands for lead-wise. Like for example, something happened in JJA or June, July, August, September. How far you can predict it? If you predict it May is good, but how much it's good for the decision making? People want it beforehand, like April or May, so that or March. So we kind of compare the different skill score, different way, all those African countries which they are interested. Top of that, I was thinking like, let's go back and look the California, this year is a very unique, right? So I was thinking about this 3-category forecast, which is issued at October and November, and the probability of exceeding the 80th percentile. And what I found, there's a lot of signal capture compared to this, the actual happen, but we also have a lot of false alarm on the Washington, which was not flood. So it's kind of a trade-off kind of thing. And that's what I say, it's a very tough problem to solve, but at least this is one of the forecasts which captured this signal. And I was, coming to next slide, I was in a project with the Department of Water Resource from California, where they are kind of interested of this kind of things because they want to take this forecast and then tailor to their, reservoir operation and make that way. And while working on that, I was found that almost 5-6 years, there is a drought in California. And then something happened this year and the whole scenario changed. And while looking at that problem, I was looking very minutely and I see this thing, which is very interesting. Like this is like January 3rd and this is January 10th. And if you think just a 1 week rainfall change everything, like red is like drought and suddenly comes to like pale yellow. And that's what I was thinking, the importance of this sub-seasonal prediction. Like in a season, you can say like, oh, there's a lot of rainfall. But think about people, I give the forecast at October and there's a January 2nd, people say, oh, there's no rainfall, right? And then suddenly next week is changed. So that's what I was thinking about this scale, like estimates. Project, and we kind of, again, set up experiment and a lot of different things. But this is kind of the skill. And GROC and RPSs, again, is a lot of technical term, but GROC are skill score which tell you whether your forecast able to capture different category. And RPSs, you can think about a root mean square error, but in a probabilistic space. Whatever greater than 0 is good or less than 0 is bad. So what we found, week 1, week 2, week 3, like you will see about the those longer lead, you lose the skill. It's not because of the magic of machine learning, it's because the predictability issue. Like week 1 is mostly weather forecast. We are very confident of weather. But week 2, week 3 is like, so when I show this thing to Mike Anderson and others from DWR, they say like, yeah, we understand the problem. But you know what, week two is also very important. So how we make this information in such a way they can use it. So I was thinking about combine these 2 weeks. Let's make it week 1 plus 2 and make 2 plus 3. Instead of predicting 7-day average, let's predict the 15 days average. And week 2 plus 3 is as important as them as week 3 plus 4. So they said, oh, that yeah, we can use it. And most of the skill come from the central highland here, and the southern part is like desert. They don't care on that part. So it's kind of a fair amount of skill that they can use. So I think like on that, like, I want to conclude this part. So this part talking about subseasonal to seasonal forecast, and there's some traditional method, but we use a machine learning method, which is it's not like we want to use because everybody will use it, like because we stuck some point. So that's what we use it, but we need to modify the system. That is very important. Like a lot of modification come in machine learning from the image processing side of view. But I think for climate point of view also, because we cannot just use that model as it is, we need to modify a lot and then we can use it. So on that, I almost end, and I think I am good with the time, or 1 minute or 2 minutes. Okay. So this is like, I think you like it. So this is one of the important aspects of the tools. I show a lot of different things, right? Like unless it's reproducible, nobody believes. So I feel like make a tool and send it. And my engagement with the WMO, where we talk about this thing to different country, like they make their forecast, nobody know how they make it. How can you reproduce it? And that's what I make. It's a very interesting thing. It's a student internship. When I was in Colombia, there is a student came and he has a different interest. Then we start with this, and we make this whole Python package. And Kyle Hall is the student, and now he joined NOAA PSL at UFS group. So yeah, it was a very good thing. And we after that, we still developed this tool. And now I don't have that slide, but like some of like NCAR, different universities, and some national meteorological and hydrological centers in Africa, Europe, and Asia, they use it because they find there's a lot of Python package, but none of the package can take care of the problem you're facing. First of all, multi-dimensional data, right? You're not having a tabular data. Top of that, the whole computational time. It takes forever to use any kind of, let's say scikit-learn. You download the scikit-learn, you have a data. So we add a method called Dusk, which is parallel the process. So you make that tool such a way that you can run in your laptop up to the cloud. So that's kind of my side project. It started like a passion, and now I use it a lot, and people use it, and people kind of, report their error and other things. And other project, which like out of time, I can talk like 2 days, but one project I want to explain, a build project where Christy is a PI from the city side, and they have different motive. And one of them is like upgrade the NOAA water model, which is giving the stream flow. And I was PI on that part. And this kind of a weather forecast, like come from climate projection here, like weather forecast, working with the people from the Office of Weather Prediction and Hydrology and Summer Forecast System. Another project is really close to what I do, called hybrid prediction of seasonal outlook of heat extreme, which is again series IRAP. Like I kind of try my luck and I win that project, where I kind of making a system where you can predict how many days will be above the threshold or how many days will be heat wave in a season, which is the idea comes again, stakeholders apart. Its idea comes when you're in a meeting with the National Heat Health System, or NIHHIS, like they are talk about heat and health. And they said like, we got a heat wave, advisory, but just 1 week or 2 weeks before. Why don't you give like a 3 months before so that we can make our things? So that comes that idea from there. And I also work on a method called digital twin, which is replacing NWP, but using deep learning. And that's what I have connection with UT Austin and others. And obviously the downscaling part is still going on. So these are like the project I was involved, except this 2 big project. And almost end. So I always love this take-home message. So the way I kind of explain my career, and it's so interesting, I found the exactly same cartoon. So it could not be like very different statistical environment. I have to grow, I have to learn a lot. And that's what I find this excellent in like the collaboration, the power of collaboration. And I can give you like, I'm the best example on that. Like I collaborate the people from here, the gurus, and then kind of understand my understanding and try to complement them so that they can use my understanding and I can use their domain knowledge. And another thing for like the early career and young students, like this whole buzzword nowadays, like AI, ML, people just use it because they need to use it. But I love to spend more time on the explainable part. Like you need to explain why the model doesn't work or why the model works. We spend a lot of time like why the model doesn't work, but none of us spending time why the model works. And that's kind of the thing I was mostly interested, like the explainable part of the AI. Otherwise, it's just like a black box of other. So on that note, thank you very much, and really looking for it our collaborations. And I love this. Anybody I put that answer, but I thought this is a dense random forest decision tree and make it so much I feel like somebody draw it, but it's actually come from my computer code. So machine learning also have a beautiful design part of it. So don't always blame it like a black box. It's also very beautiful. And ending with this advertisement, we have a postdoc hiring at NOAA PS7 series, which we are looking at the fire weather focus S2S. Very happy if you know someone or you want to apply it, or the students you want to pass it through, it will be very. Thank you very much. Oh, 12. Okay. No question. No time for question. Yeah, sure.
We are also trying some sub-seasonal fire predictions around here. And then there is this particular statistical problem of a particularly bad fire season is when you have a big green up. So you have had you have an abnormally high season for moisture. Mm-hmm. But then that quickly turns around and dries after a series of droughts. And so you're sort of looking at where do we go from peak distribution at the top to peak distribution at the bottom in the shortest amount of time. I don't know if you have any thoughts about sort of that, finding that particular signature in some climate data sort of at different scales.
That's really good thought, but I would say that's very new for me also because I never worked in fire. So, and in fact, we are looking like whoever working in fire, we found is some group in GML, they do a lot of fire working. So maybe Chris, you want to say about the fire thing and series?
Yeah, there's a ton. And I'll introduce you to the people that are probably most relevant to that problem, like on September 15th, and if not otherwise. Because there's across NOAA, and this is one of my purposes of having these kinds of talks, is there's so much work going on across our organization that is overlapping. And so there's groups in GSL and PSL working on these predictions, fire predictions from the weather scale onto the seasonal scale. And I don't know what they're considering, but that's why we need to have more discussion. So, and so Nachiketa is leading this postdoc, but actually I think the person's going to work with Melissa Breeden. Is that right? So Melissa is one of the main people that knows that.
Is it possible to try to organize a series only fire geek out?
I will do that in so many ways.
Okay.
We should talk. I mean, it's one of the reasons why even just across the university, there's so much overlapping stuff. And that's why we're having the get together on September 15th, just to learn what's going on. But we should have a separate series series meeting.
Yes.
I totally agree. Yeah.
And there are folks who are online too, who also work in this space, who I just want to highlight. And I'm not sure who all is on.
I saw Lily.
But if Lily's on, it's probably worth you connecting, the two of you connecting as well. We usually get half and half. I'd say there's probably, if there's this many people in the room, there's this many people online.
Yeah, I would also connect Melissa and Rochelle, who are also working on that to you.
Yeah.
And Rochelle was a series now, I think she will transition, but she do a lot of weekly scale fire weather. They are like a subject matter expert. So my involvement here, the deep learning part. So we are thinking to use the GFS output, the NOAA model, and try to tailor with different index of fire. And I will help them which deep learning method is choose. I'm not a subject matter expert again. So yeah, I will. So
yeah, I was more thinking about just looking for that statistical signature of when you're going from max to max, when you're going from outlier to outlier. And so
That is, yeah, because just like, just let you one thing, like you're talking about earlier non-linear, like last 3 years, there's a La Nina and suddenly it's El Nino. So that kind of change also impact a lot. So kind of similar, like suddenly the moisture became dry, like that jump is very hard to get actually.
Also too, it seemed like you were treating in most of your models precipitation and temperature independently, but like in order to, I think, fully capture the phenomenon, it's almost like you want to do a multivariate prediction too, temperature, precipitation, and also probably humidity levels, VPD. So like that would be my like ideal constellation of
That's
weather
perfect.
ingredients.
Yeah, perfect. So just let you know, like the project I explained here, like new project. First one, where we are actually not dealing with rainfall temperature, solar radiation, humidity, and everything. And like that's the problem actually. Like when you fit independently, there's no relationship. So after that, we use a method called reordering. So reordering, like the popular reordering method is Shaki shuffle. Like you kind of using reordering such that the spatial and temporal correlation is keep that. So correlation between different variables, correlation between the space, and also the time. So we use that reordering after that. So I did not explain that here, but we do a lot of different things, and it's very like physical problem. We cannot deal with independently.
Yeah, just out of curiosity, would the GAN be a potential approach to identifying those seasonal patterns as well?
Yeah, that's what like I use GAN for climate change, because GAN, the way GAN works, it depends on what you want to achieve. So I set up a GAN, and my target is not only produce the rainfall. My target is like produce rainfall at 6 different watershed and keep that correlation. So I keep everything as a set up my experiment, and it train until unless is achieve that goal. So I use GAN for that spatial correlation, but for this like a smaller scale, like here, subseasonal. For GAN problem, I have like 60 years of data of 365. Think about the data size, which is not big, but at least bigger enough to train the GAN. For subseason, I have only 20 years of data. And that is also for each grid point, it can have only 20 data points. So I cannot use that GAN because it will be overfitted. So I was thinking like independently and then kind of using shuffle to reorder that correlation.
I have another question, in a different direction, which is that I've been doing some looking at like cascading natural hazards, and so specifically post-wildfire landslides, but basically we have the fire and it totally changes that that watershed function that you have in your models, and it changes it in such a way that often the stream gauge gets knocked out, so then we don't have any data. And so I guess I'm curious if you have any suggestions for trying to pull out the ways in which those like something like wildfire might affect those like watershed functions.
Yeah, so I think like 2-3 years back, we were thinking about these compound extremes, like how one extreme impact others. And we were thinking about incorporate the antecedent conditions. Like instead of just using this climate data, I just use the antecedent condition. But again, this is another thought I have, but you don't get that chance to work on that. So yeah, that's a really, but I don't, yeah, it's tougher problem, but it's always better to including that kind of information. And the way I was thinking at a statistic point of view, like you kind of update your prior information based on the posterior, right? Or sorry, posterior information based on prior. So basically a Bayesian network where kind of update your like information based on what happened recently. So no, that's, yeah, I don't have any answer on that because I did not work, but that's a good answer.
Great proposal.
Yeah, well, yeah, I've been working on this project trying to use like data assimilation with the dynamical hydrologic model. But it is incredibly computationally expensive. It's really absurd. So
totally agree. Okay.
Thank you.
Thank you all.